Okay, I will get started. So we're going to see a number of scenarios where ParaView is actually doing parallel processing and parallel rendering. Recall that this morning I talked about the visualization pipeline being not only about rendering, about making images, but also, and perhaps predominantly, about making feature extraction, data filtering, data processing. Excuse me. So sometimes it's not so much the final step, the image rendering, that has to be parallel, but it's mostly the part of the pipeline that stays above or ahead of the image generation. There was a question in the chat during the lunchtime. If you do not have a GPU, does it really make sense to use the ParaView pipeline anyway? And my answer was that for the multi-core allocation, we have a special version of ParaView, which actually uses an LLVM-based parallel rendering layer, which is actually very fast, especially on polygonal models. So it might have some restrictions about volume rendering, but for this, I've also published a couple of years ago a paper in the Parallel Processing Journal, which shows how ParaView as an Osprey-based rendering layer for parallel volume rendering, which is also completely concurrential with the hardware accelerated volume rendering implementation on the GPU. So in most cases, really, the rendering is not the bottleneck. All right, let's go on. Excuse me. In the classical way of using the ParaView desktop with a remote server on Daint, via the graphical user interface of ParaView, we instantiate, we create a Slurm job, which will instantiate, which will allocate a particular set of nodes with different options. And this allocation is done through an SSH tunnel, such that you can connect yourself from the outside world through the CSCS firewall onto the logging node of CSCS, and then onto the compute nodes allocated for the task. So the page I have here on display would show what the classic allocation would look like. Here's an example where we would allocate one node, one compute node, with 8 MPI parallel tasks running on the node, sharing the GPU. 20 minutes, partition, etc., constraint, GPU. And then the command that is run is actually srun, PV server, which is the name of the executable for the ParaView server on the server side. RC is a special option, which means reverse connection. And we'll explain what that means. Then the CH option is the client host. In this case, it's the name of the logging node on Daint. And then there's a special option, SP, which is a number. It's a port number through which we establish the SSH tunnel. And this is why in our documentation, we tell each person to use its own user ID, which is a unique number, such that SSH tunnels do not collide. They are allocated on different ports there. So what happens in this standard scenario of connecting a desktop ParaView with a remote server running on Daint. The desktop, your desktop ParaView would create an SSH tunnel using this particular number onto the logging node of Daint. Once the job has started, the PV server by default connects back to the logging node, and because of the SSH tunnel, the logging node forwards the connection request back to your local desktop, and the connection is established. So that's the classic connection method. Let's see now how it works in the Jupyter node side. So we've looked quickly at this example already this morning. Basically, what we do is on the allocated compute node, in this case here on the right side, I see that my prompt is need 03173. That's the name of the compute node allocated for this particular book. I run my PV server with 8 tasks. So this is running locally on your compute node, sharing the GPU, because as you know, on Daint, we have a single GPU per compute node. And as I run the PV server like this, it puts itself in a waiting state, which is over here, the third line, accepting connection on this particular port number, 11,111, which is the default port number. On the Jupyter Notebook side, connecting, which is this command here, to the local host, which is local, will in effect connect to the PV server side. And this is why as soon as you emit this connect command, the server responds with the message client connected. And by the way, as you see here, just below the cell number 2, the message that returns is connection is established with the local host with that particular number, 11,111, which is the port number which the server side used to create the connection. There. So basically, it's very parallel to the way the desktop SSH tunnel-based connection works, but here we do it locally on the allocated node reserved for that particular notebook. I will demonstrate that in the page in a moment. Let me go to my next slide. Now, in the case that a single compute node is not enough to treat your data, then you would have to allocate more compute node. So you can do this within your own primary allocation. And this is what the next notebook demonstrates. The notebook called Volume Rendering Parallel Nodes does an extra node allocation. And then it uses the same principle whereby the client, which in this case is the notebook itself, the client requests a connection to the first task on the first node of the allocation. This is why in my notes here, for this particular example, of course, every time you do a new allocation, the name of the node might change. For this particular example, I'm connecting not to localhost anymore, but I'm connecting to a different need number, which means a different compute node. So let's see this in practice. I'm going to switch sharing desktops. Okay, so you should see now my first Jupyter notebook called ParaView Volume Rendering with parallel tasks on the local node. So I'm going to again do my ParaView import statement. In the meantime, I'm going to create a terminal you can put here on the side. Now, the ParaView module has already been loaded from the default startup command. So if I do which PV server, that server indeed is known, and it comes from the ParaView version 5.90 installation on Daint. So I can simply run PV server with the number of tasks I wish to run. So for example, 8 or 4 or whatever, 8 PV server there. Notice that I am running on the compute node called need 01959. On the default port 11,111, the compute node is waiting for a connection. I come to my Jupyter notebook, I connect to the local host, and we called it this morning. I said that quite a few seconds here need to pass by between the to make sure we have a clean connection. This is a little bit of a bottleneck at the present time. There, we are connected effectively on port number 11,111. I will now get some information about my connection, such as the rank and the number of processors allocated. And if rank is 0, I'm going to print the version, a number of statistics about my connection. There I am connected to the Tesla 100 GPU. I'm going to read a data set which comes from, it's a data set that was provided to me by NVIDIA for demonstration purposes. Okay, so I'm here giving credit to the NVIDIA people. This data set is a floating point array of size 2048 by 1024 by 1024, floating point number in raw format. What does that mean? It means that to open this data set cleanly, I use the so-called image reader of ParaView, and I must specify both the float and the endianness and the extent of the grid. Now, the extent of the grid in ParaView, in the ParaView vocabulary, means the dimensions, but the dimensions always start at 0. So we have to be a bit careful here. If the volume of data is of size 2048 by 1024 square, then the extents are indeed 0, and then 2048 minus 1, 0,024 minus 1 for the y direction, and finally the z direction. So I'm going to read this, and this reading actually takes place in parallel. Recall that we have here on the right side of my screen an allocation with 8 PV servers. Now, in many cases in ParaView, if you use one of the standard reader, ParaView knows how to distribute the data very intelligently in a very load balanced fashion between each PV server. So in this case, even though here, this statement could be also executed on a single task. If I execute this in parallel, then I can be guaranteed that each PV server actually read only 1/8 of the data. I will now create my active view. And as I do this, I should have a message from my server side. I don't see anything. There we go. There was a little bit of light. So there we go. The 8 servers have recognized the call to create a view. So each of them will now render their private part of the data, and then the images will get composed and sent to the client. The client, in my case, is the Jupyter notebook. I will get my PV display widget. There we go. And if you've noticed here, I've used the representation mode called outline. So the outline is basically just the bounding box of the volume, which allows me to place the volume in the best position I wish before doing the heavy rendering of the data. Let's look at which representation styles are available. One of them is volume. That's the one I'm interested about, to do volume rendering. So I will turn it on in this particular fashion. I will select the scale field called image file and the particular lookup table which I have defined earlier. For volume rendering purposes, I need to define a scale opacity unit distance, which I set here to 4, and then I execute that particular rendering. So there, it takes more or less a second or two to initialize, and this is a volume rendering. Now you could say, well, how do we know that it's actually running in parallel? We could try to change the representation to surface mode, like this. And we could color the data. I would have to do this like in this fashion, color by rep, with the variable called VTK process ID. And as I do this, I probably need to rescale my color, so I'll have to think about how to do this. in the interest of time, I'm going to leave this notebook open and go to the next one, and then if we have time at the end, we'll come back. Okay. So the second point I wanted to address is how to do a second allocation to augment the number of nodes available for the data processing. So this is my next notebook over here. Perhaps I can stop this notebook momentarily, and I will go about, let me disconnect here. Yeah, in fact, I need to disconnect to get back my terminal window. There we go. Now, I'm going to do an additional allocation. So here I'm loading my ParaView library. Here I'm doing just like you do from the standard shell, an salloc for 4 additional nodes. This is my account name. I want GPUs. I use the particular reservation of today, the tutorial reservation, and I go for 20 minutes, which is more than necessary. And what you have to be careful with now at this time is you have to look at the names of the compute nodes allocated. And here they are. I have 4 nodes allocated, and the first one of them is called need 02380. If I were to do the following host name, there's the list of my 4 nodes, my 4 compute nodes there. So I need to connect my client to the first one on the list, which is this one, need 02380. So I will change carefully here my cell, and I will, first of all, run my PV server. It will use the default port, which is 11,000, etc. So as you can see, need 02380 is waiting for my connection. I will connect to it here on the left side of my screen. The client is connected from the server side. On the client side here, I need to wait a little bit more to make sure I have a clean state. There we go. And I'm ready to go on as earlier. So I get my rank, my information, my statistics. I read my data in parallel again. I create my active view over here. And here I should have again on the right side of my screen 4 messages telling me that each compute node has allocated a GPU, and I am now ready to go on with the visualization pipeline and the rendering. So there is my bounding box, and then my rendering will show up just like before, but running on this additional compute node allocation. Once I'm done, I disconnect from the resource. On the right side of my screen here, I get out of my allocation with an exit, and now I'm back on my local node. There we go. I'll go back to my other screen if you let me, which is this over here. Okay, you all see my PowerPoint presentation? Yes, I hope so.
Yep.
Now, there might be cases where you'd like to connect your Jupyter Lab notebook, so running locally at home or in your office, to an allocation on Daint. And in that case, the process is, I think we've learned almost all of the basics at this time. You will simply need to use a different call. Instead of the connect call, we use the so-called reverse connection, and we give it our user ID, and that's what we have to do. So this would be just like connecting a desktop ParaView application to a remote Daint allocation, except that in this case, the client is actually a Jupyter Lab notebook. So on my next page here, I have a little bit more instructions for you. On a terminal window, you would need to open an SSH terminal, select a login node. Here I've selected Daint 101 as a login node, and I open an SSH terminal with my user ID. It's a reverse terminal with this particular port and the name localhost, such that when the PV server makes an attempt to connect to localhost on the PITS Daint side, it actually sees my own desktop at my remote location, thanks to the SSH channel. So what you see here on the right side of the screen is what happens later on the PITS Daint allocation. I load my Daint GPU or my Daint-MC module. I load my ParaView, and at that time, I do an S-run with the same options we've seen before, which are the options used by the desktop method. On the desktop method, I use my standard import statement and my reverse connect. So this is a bit more specific. It's about running Jupyter Lab on your own laptop or desktop. If you have a question, if you feel like you'd like to try this, you can always come back to me later on after this presentation, and I will help you out. Next, I've talked a lot about MPI-based parallelism because it's actually the initial way ParaView was designed. ParaView was designed to do data partitioning among MPI tasks, and then each PV server actually treats one dedicated subpart of the data. However, there's a lot more than MPI-based parallelism in ParaView. There's also SMP-based parallelism. And there's actually a very efficient layer for SMP-based parallelism on the node within ParaView. And a lot of it actually happens in a very transparent fashion. On a standard desktop ParaView, there's actually quite a bit of filters already running with SMP parallelism. And in the implementations we have on PITS Daint, I have used the Intel TBB threading building blocks to implement this SMP parallelism. So we're going to see a few examples of that. The classic example I have is actually about ray tracing. Perhaps some of you have seen this demonstration before. Ray tracing is one way of doing rendering. The other would be the classical polygonal rendering. Ray tracing is a way to achieve what some people call photorealistic rendering, because we can do shadows, we can do refractions, diffractions of light, we can simulate material characteristics. So we can do something that is a lot more closer to reality. And ray tracing is actually fully multi-threaded on a local compute node. So this would be one example of SMP parallelism. At the very end of the visualization pipeline, which means the rendering end. But you can also do a lot of data filtering in an SMP fashion. So I have an example here, and I have a notebook which I have prepared for this particular purpose, which uses a series of filters dedicated to the treatment of SPH data. SPH is the smooth particle hydrodynamics method. It's basically a set of points in space without a grid structure underneath. And of course, because there's no grid intrinsically in the method, we are left out with a point cloud. However, it can be very useful to go back to the traditional grid-based rendering. And in this case here, I'm showing a slice, if you want, or a plane going through the cloud of points showing the value of the scalar field, which in this case is the density of my field. Well, in our case, the SPH interpolator is again fully multi-threaded with SMP parallelism and with the Intel TBB library. So we're going to see this example next. Yeah, just to avoid switching screens too often, I will present the second example I have prepared. There is in ParaView yet another family of algorithms called the accelerated algorithms. And those algorithms are available through a plugin. So if you use the standard desktop application, there's a menu called Load Plugin, and then you load into memory a shared library, which includes some of those accelerated algorithms. Now, the notebook I have prepared demonstrates this. This is using the same data, the same volumetric data which NVIDIA provided to me, which is this large volume of data, a grid of 2048 by 1024 square. And one traditional way to look at scalar field, I suppose all of you, if not most of you, are aware of. One traditional way is to look at isosurfaces. So contour surfaces through a scalar field in 3D. There are different ways to achieve this in ParaView. One of them is actually a method called contour. And then the second one, as we will see in the notebook, uses one of those accelerated algorithms. So on to the demonstration with the notebook.
Yep, perfect.
All right, sorry guys. Good. So my first example about SMP parallelism is this one. Yes. So standard stuff, I'm going to import my ParaView module. And yeah, this is the time to actually look at our CPU resources. So if I get to the right menu here, I'm going to put this on the side. And we're going to watch especially the CPU here, because what we're doing is not very graphics intensive, but it's very compute intensive. So I'm going to read my data here. This is a data set I have prepared yesterday evening. So it's basically a point cloud. I need to extract the first point cloud from this group. I will set up a column map for the scalar field called rho, the density. I will extract or create a representation of the point cloud. And there's my cloud. So on the screen here, we see basically a big blob of data, and way deep into the data set, if I can get to it, there is this formation of planets, which I am interested about. But as you can see, I have to really dig in deep into the data set, into the point cloud, to look at my data. So an alternative is to use this SPH interpolator. So I will now switch to this other filter. And as I do this, you will see the load on my CPU jump to really the full multi-threaded capability of the node. And the computation is done already there. So we've had about 5 seconds of all cores computing to do this interpolation. I will hide the point cloud momentarily and show instead the SPH plane interpolator. And there it is. I just need to reset my view a little bit. I need to go back to my cell number 4 for the initialization. And there I have a nice clean 2D plane interpolation of my point cloud. Now I've used a very low density for the spatial step kernels of the interpolator. If I go now to my next cell here, which is this highlighted cell, we will see again a fully multi-threaded execution of the filter. And this one should take about 10 or 15 seconds. I forgot exactly the value. And then we will see, once it's done, we will see a much more resolved extraction of the plane. So here we're almost finished with the computation, and my picture should update in a few seconds. There we go. So there we have the first demonstration of a fully accelerated filter using all cores available on the compute node allocated. There, I will stop this notebook, this kernel, and go to my next example, which was the one called large data contours. So I'm going to read the data which you recall was provided to me by NVIDIA, this large volume of data. There it is. And on cell number 4, I'm actually going to time the execution of the standard isosurface contour algorithm. So it's this one, which I'm going to start immediately because it's a large volume of data, and the isosurface extraction takes actually a very long time. I'm going to have to make you wait at least 10 more seconds here. Let's look at my resources. I want to put them on the side. There we go. You see, I'm just barely using one core of computation, and this is why the standard isosurface filter takes such a long time. Execution time, 36 seconds. I'll get my standard display widget, and I will show my isosurface. And there we go. We have here, this is the example of a supernova simulation, the explosion of a supernova. And we have here kind of a quick representation of this isosurface of density for one particular threshold. I will hide this particular object. And here's the key instructions to load my dedicated plugin. In this case, this is the accelerated algorithm plugin, which I will load now at this time. And to replace the standard isosurface algorithm, I'm going to use an algorithm called the Flying Edge 3D filter. As you can see here from the documentation, it's a replacement for the isosurface algorithm, and this is the work of mostly Will Schroeder at Kitware with some other colleagues. And as Will indicated in the documentation of the class, this class is threaded with SMP tools. Using TBB or other non-sequential type may improve performance significantly. Let's see about this. Recall that we have an execution time of 36 seconds here for the standard isosurface. We're going to run here the flying edge, and we're done. And I'm now going to contour it. I'm now going to display it, and we have exactly the same representation. And we saw it very briefly, this peak of usage of the CPU, of the multi-threads available on the node. There. Those are good, those are very good examples actually of filters which are naturally accelerated on the CPU, and where performance is really of great interest, and where the rendering itself is actually not the bottleneck. The computation of the visualization pipeline is the bottleneck, and this is where it's very important to have both forms of parallelism, the SMP-based parallelism on the node and the MPI-based parallelism on a set of additionally allocated compute nodes. So that's actually all of my demonstrations for this afternoon. We've seen how to allocate dedicated MPI-based PD servers to connect to the local ParaView client, be it a Jupyter notebook or a desktop ParaView client. And we've also seen how to do SMP parallelism. So some exams, some filters will be naturally implemented with SMP parallelism, and you won't have to worry about loading a particular plugin. You won't have to worry about how it is being implemented. It's just there and it works in parallel. Some others, such as the accelerated plugins, need to be explicitly invoked to do your computation. So by default, in summary, by default, with ParaView and isosurface computation will use the slow execution path. And if you want to be clever, you need to look through the documentation, you look at the examples, perhaps come back to me with your special use case, and we can see about finding an SMP-based algorithm as a replacement for the slow path execution. There, so that's basically the end of my presentation. I'm a little bit ahead of time, but I think we're fine. We can allow for some questions, and I will also remain available as we agreed with the two other speakers during the lunch break. I will remain available at the end of the last session so that people can ask specific questions.